Hi friends, welcome to GMK tutorials. In this video, we are going to see about the multi-level voltage scaling. So this is a low power VLSI concept series. So in this today we will focusing on multi-level voltage scaling point of view. It is the second topic in the supply voltage scaling point of view. The first one is nothing but static voltage scaling, and second one is nothing but multi-level voltage scaling. Let's move on to this topic. Before move on to the topic, I request you guys, please subscribe our channel still if you are not subscribing. Okay, thank you for your endeavor support up to now. Thanks a lot for everyone. Right, let's move on to this topic. So the first one is nothing but multi-level voltage scaling means this is an extension of SPS. So multi-level voltage scaling is an extension of static voltage scaling, where two or few fixed discrete voltages are applied to different blocks of the subsystem. Generally, in case of the static systems, where just we are applying only single voltage. If you are applying the single voltage, obviously the power dissipation may be reduced because of some general formulas will be there in terms of dynamic power dissipation, how the power dimensions can be reduced. If you see the equation generally, so power dimension, so this is power. Generally power is also a very important consideration, that is maybe so this is a very important. So as well as the basic concept behind the multi-level voltage scaling means the high VDD gates. Higher VDD gates means if you are applying the high VDD to the gates which is having very less delay, but the power dissipation is very high. Suppose if you take the another consideration, that is nothing but low VDD gates have larger delay but lesser power dissipation. This is one of the key important topic you have to remember throughout this lecture series in case of the multi-level voltage scaling, because of based on this one we will perform different operations. So generally the total power consumption can be reduced without degrading the overall circuit performance. That is also very important. Suppose if you are designing any circuit, the overall performance may not be degraded. In case if the performance is degraded, that is also one of the limitation in that method, right? So for that purpose, without degrading the performance, we have to move on to the next one. Let us see the next one. So micro-based voltage island methodology targets. So generally we have a two different methods will be there, that is discussed in this. One is nothing but micro level, and second one is nothing but standard level. So these voltage islands having a different granularity, the overall circuit performance. So with granularity. So let us see the first one. Micro level means here micro-based voltage island methodology targets towards a entire macro or maybe functional block to be assigned to the operate at a different voltages at the time of the high level synthesis. Generally high level synthesis having some techniques that transforms the behavioral model into the RTL model. That is also seen in the architectural approaches point of view. So in this scenario, starting with the intermediate representation is known as a DAC. So DAC means a directed acyclic graph is a representation for the DAC. So high level synthesis involves two basic steps. Generally in case of the high level synthesis also two basic steps will be there, that is very important. First one is nothing but scheduling. Generally the scheduling refers to the allocation of the operations. Scheduling refers to the allocation of the operations to the control steps. That means at which time the operation is going to be performed. That can be generally mean the scheduling. As well as a control step is a fundamental sequencing unit in a digital system which corresponds to the clock cycle. So coming to the second important thing is nothing but allocation. Allocation means involves the assigning the hardware requirements or assigning operations to the hardware. That is allocating a functional unit, storage units, and a communication paths for the corresponding task. So these are the two important important steps in the high level synthesis. After scheduling step, some operations will be on the critical path, whereas some operations in the non-critical path. Depending upon the critical path as well as non-critical path, we can apply the different supply voltages to the critical path as well as the non-critical path. So that plays a very important role in the multi-level voltage scaling. So let us see how this is very important. So let us see this diagram. So this is just a macro based voltage island approach to achieve the low power. In this scenario, just a plus 1 plus 2 multiply. So where 1 represents the multiplication, 2 3, these are the multipliers. That means if you are performing any multiplication, let it be considered A, B, like this. The first at a single step it will perform solve the multiplication process at step 1. At the step 2, the first and second multiplications are going to be added operation. In the third step, the third multiplication result is added to the last adder. This is nothing but where third multiplier is a no criteria. That means it is not very high priority. That means it is not no need to perform immediately in the step 1. Maybe it can be performed in the step number 2. That means this multiplication carried out here, then we can add these results also. But if you are doing like this, obviously the first multiplier performs the addition of the multiplication of the first one. The same first multiplier can be used for the third multiplier also. But if the time being we are considering 3 multipliers, so 3 multiplication operations can be carried out in the initial stage. That means step number 1. In the step number 2, the first multiplier output and second multiplier output going to be added. In the third stage, third multiplier output and whatever the previous output is going to be added in the third step. This is a scenario based on this one. The first step is maybe some critical path and second one is in the non-critical path. So critical path means it is a very important role. Based on that one we can assume. So suppose if you are treating this one, this part is generally critical. This is nothing but a non-critical path. Okay, this is non-critical path. It is nothing but a critical path. So higher critical path circuits can be operated with a high level voltage and non-critical path circuits can be operated with a low level voltage. Because of that is very important concept. Let us see how it is very helpful. As the high VDD gates have a less delay but the higher dynamic power and static power dissipation. Because of we know that generally power dissipation plays a very important role. So let us see this one. Generally you know guys. So dynamic power P is equal to alpha into CL into VDD square into F. That means if the supply voltage VDD is rises, what happens is that obviously this power dissipation is also increases. That means this supply voltage plays a very important role. If you are rising if high VDD gates, obviously less delay, because of it is also related to delay. Delay is directly proportional to VDD into 1 minus VT by VD. This formula is already well known everyone, right? Square will be there. That means if the delay is increases based on the supply voltage. That means both the delay parameter as well as the power dissipation parameters are directly or maybe inversely related to the supply voltage. That means if you are reducing the supply voltage, obviously the total power dissipation maybe decreases, as well as if you are reducing the supply voltage, the delay is also increases. That's why it is plays a very important role. So that is a basic thing here. Let's move on to the next one. Just I will rub it. So let us say in this situation, so this is a while the main intention is nothing but high VDD gates have a less delay but high dynamic power dissipation. So that is the first point already visible in the starting of the slide itself also. As well as while the devices on a non-critical path shall be assigned to the lower VDD. So we have to apply the high VDD voltages to the critical path as well as low VDD supplies to the non-critical paths. Therefore, the total power consumption can be reduced without reducing the performance. That is the first overall important point in this situation. As well as in the figure 14, figure number 14 shows the total delay, how the critical path is at 10 nanoseconds as well as the non-critical path. So that will be seen very next slide. Let us see this, move on to the next one. So this diagram shows the assignment of a multiple supply voltages based on the delay and a critical path. So in this diagram, the red color line shows that it is a critical path. This green color line shows the non-critical path. This is nothing but a non-critical path. The first one shows the critical path. The critical path can be assigned as a high VDD voltage as well as non-critical paths can be assigned as a low VDD. Suppose if you are observing in the 8 nanoseconds point of view, these gates are applied to the only VDD low. VDD low means these gates are operated at a non-critical path, so therefore we have to assign a low VDD voltage. Therefore, if you are assigning the low VDD, obviously the delay may be increases, but power dissipation will be decreases. So that is the one of the advantage in the non-critical path. So that is based on that one we can assigning the situations, right? So coming to the in the standard cell, second one is nothing but a standard cell. First one is nothing but macro based. So in the standard cells, gates on a critical path, non-critical paths are clustered into groups. Suppose if you want to apply some power supplies to the any circuit with different gates in the critical path as well as non-critical path, we need to apply the part of the circuit can be applied as a low voltage, or maybe the remaining part can be as a high voltage. So for that, at that time, it is very difficult to apply different voltage sources throughout the circuit. So for that purpose, we have to segregate the non-critical path into one part and the critical paths into one part. Then it is easy to apply non-critical paths with low voltage and critical path cells with high voltage. So this approach will be very helpful for assigning the corresponding supply voltage. As well as one of the important point, let us see in this one, this approach modifies the normal distribution of the path delays using a single supply voltage in the designing of the distribution of a path delays in the. So that means, moreover, one more important point is nothing but, let us see here, the use of multiple supply voltage results to, if you are using the multiple supply voltage, results to reduction of the dynamic power from less than 10 to 15% with an average of about 40%. That is one of the most advantage of the multiple VDD scaling. As well as, if you remember, one important point is nothing but, in case of the multiple VDD, just we are applying multiple voltages, but very important criteria is nothing but just you have to apply only 2 voltages up to. If you are increasing the more than 2 voltages, obviously the performance of the circuit is not up to the mark also. If you are using only 2 voltages, therefore this performance may be good for the corresponding system. That is also very important consideration you have to remember, right? So this is nothing but a cluster diagram. If you are closely observe this diagram, where the cluster diagram, the left, this part is generally called as a VDD H cluster and a VDD L cluster. Already we discussed in the previous slide. This line, whatever this dark line shows that it is nothing but a critical path. These critical path gates are there. Whatever the critical path elements are, flip-flops, whatever it may be there, that can be applied. That is applied with a high VDD voltage. Okay, the critical path gates are supplied as a high input voltage, that is nothing but VDDH. As well as non-critical paths will be there. That path is also operated with VDD-L voltage. That means low VDD voltage. Why? Because we are applying in this scenario, we know that generally high VDD voltages having a lesser delay, but a power dissipation is more. But if you go for the non-critical path point of view, it exhibits the very less power dissipation, but delay may be increases because of non-critical paths. Delay is not an important criteria, but overall critical path delay is very important consideration. That kind of non-critical path delay cannot exceed the critical path delay. So that is a very important point you have to remember. So this is nothing but distribution, single supply voltage scaling. It is nothing but multiple voltage supply. So this is the critical path delays. So this is nothing but MVS. In this scenario, the critical path can be shifted to in this direction, right? So this can be achieved by applying the very low voltages in this case. So that means if you are applying very low voltages, obviously low voltages means that we are supplying very less voltage to the corresponding circuit. If you are applying less voltage means the delay is also increases. Therefore, the distribution of the circuit is in this direction because of that. As well as extending the approach more than 2 supply voltage yields only small incremental benefit. The major gain is obtained moving from single voltage to dual voltage. So that is very important point. In case of the previously, we know that generally we are approaching a single voltage supply. At that time, the benefit may not be very good up to the mark. But if you go for the double voltage or maybe single VDD to dual voltage, it has been observed that dual VDD single VT system optimal VDD is 60 to 70% of the VDD. The optimal supply voltage depends on the threshold voltage of the mass transistors also. Correct? So the optimal voltage is also decided with the corresponding transistor threshold voltage. So because of the whenever the gate is on, at that time only the corresponding throughout operation can be carried out. So that's why the threshold voltage is also plays a very important role, right? So coming to the challenges in MVS. So up to now we are discussing different points in case of the MVS, where MVS means that suppose let us see this is nothing but in case of the single voltage, just we are applying some VDD like this. Okay, so this is nothing but a subsystem. Okay, so in this subsystem we are supplying only single voltage. Why? Because in case of the subsystem we are reducing the supply voltage. Generally in the previous class we know that if you are reducing the supply voltage, obviously power dissipation will be decreases. So the basic concept here is nothing but if you are taking a very complex system, at that time different subsystems will be there. Different subsystems may be operate for different voltages. So if you are identifying it is maybe operate for 1.2 volts, it may be 4 volts. So depending upon this one, we have to provide such a kind of the suitable voltage. Obviously we can reduce the power dissipation also. So the basic intention of this multi-level voltage scaling is nothing but just we are providing a more than single voltage for the subsystem. Therefore overall power dissipation can be reduced, as well as if you are applying the high VDD for critical path, we can reduce the delay also. If the delay is decreases, means the performance of the system increases. That is the basic intention behind this one. So coming to the challenges in the MVS, let us see the challenges in the MVS, challenges in the multi-level voltage scaling. First one is nothing but a voltage scaling interface. Because of in this video previously we've seen that if you are applying the different voltage like 1.8 or 2 volts, obviously it is not possible to directly apply the corresponding each and every circuit. For that purpose we needed some level translators are required in the circuit. So that's why voltage scaling interfaces are required, as well as converter placement. If you are placing a converter, where we need to place, that is also regarding the converter placement, floor planning and routing issues, as well as multiple supply voltages we need to provide to the circuit, and static timing analysis, as well as power up and power down. That means if you are power up the corresponding network, what is the switching activity, what is the sequence of operation, those kind of the things also we need to consider, as well as the clock distribution. These are the some of the points related to the multi-level voltage scaling. Just I will explain in Telugu also, okay, with a very quick revision. So I think just we will discuss in Telugu in the separate part will be there in the if the time being will be there, definitely we will discuss in Telugu also very quickly, right? So thank you for watching GMK tutor. Thank you. Goodbye.